In grand canonical distribution, we know P n j so we have obtained the probability of a system having n number of particles in state j having energy Ej. We define this by P n j, which is nothing but e to the minus beta E n j times e to the minus gamma n, and in the denominator we have the grand canonical partition function. Okay, and the grand canonical partition function. So the grand canonical partition function is we define as this by theta, capital theta is sum over n, sum over j e to the minus beta E n j times e to the minus gamma n. So since we obtained the partition function, we can calculate different thermodynamical properties like average energy we can calculate. So if we calculate average energy, we know the expression for average energy. So the expression for average energy is P n j times E n j, and if we carry out this one, we get so if we differentiate log of theta with respect to beta or with respect to temperature, we get the expression for average energy, which is very similar to the one we obtained for canonical ensemble. We can also calculate average pressure. So average pressure is nothing but and if we carry out this, we get the expression like so we get average pressure is Kb times del ln theta by del V, where beta and gamma are constants. Here we can also calculate average number of particles in a given system. And we arrive an equation so if we differentiate ln theta with respect to gamma, keeping V and beta constant, we get average number of particles in a given system. So, and now we can calculate other thermodynamical properties we will discuss now, but before that we will see what is gamma. Okay. So, what is the value of gamma we need to calculate next. Okay, so let us consider a function f is function of beta, gamma and all energy values, and this is so f we consider ln theta, and theta we know theta is the partition function or grand canonical partition function rather. So, first we consider a function f which is ln theta. Okay. Next what we do, calculate df. Df is del f by del beta, keeping gamma and all enj values constant times del d beta plus del f by del gamma times d gamma plus so the third term is sum over n sum over j del f by del e n j times d n a d e n j, keeping beta and gamma and e n j's. So here we consider we are keeping constant of all e n j values, all e n j values, all e n j's except the one we are differentiating with. Okay, so we get df is del f by del beta times d beta, gamma and e n j are constant, then del f by del gamma times d gamma, where beta and e n j's are constant, and plus sum over n sum over j del f by del e n j times d n j. Here we constant beta, gamma and all e n j values are constant except the one we are differentiating with. Okay. So we can further simplify this expression as df, and this first term is nothing but average of energy. The second term is nothing but average number of particles, and the third one is giving us beta times P average times dV. So we get df is minus E average times d beta minus n average times d gamma plus beta P average times dV. Okay. Now what we do? We can further simplify the above expression like this. So here we have added in both sides, we have added few terms. Okay, the same terms we have added, and then we arrive at this expression. Now from thermodynamics, for open systems, we know TdS is du plus v dv minus mu dn. So this extra term is need to be incorporated for open systems. Okay. Now if we compare expression 1 and expression 2, the coefficients we get gamma is, so comparing 1 and 2, comparing equations 1 and 2, we get gamma is minus mu by kVt. So this is the value of gamma. Okay, so suppose this is our equation 3. Okay, now what is the value of entropy S? S is, so if we do the integration of equation 2, we get S is E average by T times N average by mu, N average times mu by T plus KB ln theta. Okay. So, this is the expression for entropy. So, this is our equation 4. Next, we will discuss something very interesting thing, like we have what we know grand canonical partition function. So, here we substituted the value of gamma in this expression. So, now what we do, so sum over n will be there and sum over j e to the beta e n j, the first term gives q this. Okay. So, grand canonical partition function is nothing but canonical partition function plus all possible values of n. So, grand canonical partition function can be represented as canonical partition function plus all possible values of n. Next, we can also calculate G or Gibbs energy . So, G is nothing but mu times n. So, you get E plus PV minus Ts. So, we know this, or you rather here. Okay. And PV is mu times n average plus T times n average minus E average. So, if we further carry out, we get PV is KBT ln this. Okay. So, we have discussed a grand canonical ensemble so far. Next, we consider, or next we will discuss microcanonical ensemble. So, in microcanonical ensemble, number of particles is fixed, volume is fixed and energy is fixed. Like in canonical ensemble, number of particles fixed, volume was fixed and temperature was fixed, and grand canonical ensemble, chemical potential, volume and temperature, those three are fixed. In microcanonical ensemble, number of particles is fixed, volume is fixed, energy is fixed. Since energy is fixed, so these three are fixed. Okay, since E is fixed, okay, so you can write E1 plus E1 equals to E2 equals to E3 and so on, and we suppose we have omega number of states, so omega. So, all states are degenerate. So, very similar to the particle in a box, consider a particle in 3-dimensional cubic box, and for this, for particle in 3-dimensional cubic box, suppose we have nx, ny and nz values are 1, 2, 1 or 2, 1, 1 or 1, 1, 2. So, these three states, energy of these three states are the same, so they are degenerate. So, these states are degenerate. Similarly, here since E is fixed in microcanonical ensemble, so E1 equals to E2 equals to E3 up to E omega, where omega is the number of states of degeneracy, all states are degenerate. So, one would expect that P1 equals to P2 equals to P3 equals to P omega. Means probability of having state 1 with energy U1, we define this one as P1 or equals to P2 equals to P3 equals to P omega, where omega is the degeneracy as I mentioned. So, omega is function of N, V and E, the degeneracy. So, as I said, since energy, so whatever I said is like in microcanonical ensemble N, V, E fixed. Since E is fixed, so E1 equals to E2 equals to E3 up to E omega, where omega is the degeneracy. So, since all energy values are the same, so one would expect the probability of having all the states the same. So, we are going to prove that probability of all the states the same in microcanonical ensemble. Okay. So, for this we start with the expression S. We know S is Kb ln W. This we know from thermodynamics. Okay. So, what is W here? So, W is factorial n by n1 factorial, n2 factorial and so on. That we already studied, we know already. So, we get S is Kb ln n factorial minus Kb ln n1 factorial minus Kb ln n2 factorial and so on, right. So, we get S is Kb. Now, we apply Stirling's approximations. Okay. So, applying Stirling's approximation, since all the n values are very large, so we will apply Stirling's approximation and we get S is Kb ln n factorial gives us n ln n minus n. The second term gives us Kb times n1 ln n1 minus n1. Third term gives us Kb times n2 ln n2 minus n2 and so on. So, we get S is Kb n ln n minus n minus sum over I ni ln ni, and then we have plus sum over I ni. So, we get S is Kb n ln n minus sum over I ni ln ni, because n and sum over I ni they cancel each other. Okay. Next, we know S is Kb times n ln n minus sum over I ni ln ni. Now, Pi, probability of ith state, is nothing but ni by n. So, it gives us ni is n times Pi. Now, if we substitute the value of ni here in the expression of entropy, we get S is Kb n ln n minus sum over I So, we get S is Kb n ln n minus n Pi So, we get S is Kb times n ln n minus sum over I n Pi times ln n minus sum over I n Pi times ln Pi. So, we get S, we can further simplify and get Kb, S is Kb ln n minus n ln n sum over I Pi minus n sum over I Pi ln Pi. So, sum over I Pi gives us, this gives us 1. So, n ln n and minus n ln n sum over I Pi, they get cancel each other. So, we get S is minus n times Kb sum over I Pi ln Pi. Okay, now, the statistical entropy S is minus Kb So, we are using a dummy variable j here, j goes from 1 to omega because we have omega number of states in our system. So, Pj ln Pj. So, this is the value of statistical entropy. Okay. So, what we do now, we calculate ds. Okay. ds is minus Kb So, we get ds, if we further simplify, we get ds is minus Kb sum over j goes from 1 to omega the Pj ln Pj plus 1. Now, what we do? We maximize entropy, okay? Because for an isolated system, so microcanonical ensemble is presents isolated system, right? Because number of particles is fixed, energy is also fixed. Okay, so both matter and energy exchange are not permissible. So, for an isolated system, at equilibrium, so an isolated system and equilibrium is one of maximum entropy. So, this we can learn from second law of thermodynamics. So, basically we are now maximizing W, okay, maximizing S. So, Next we are maximizing entropy. So we get ds if we maximize, we get this. Now we will simplify above expression, like we have the constant sum over j pj, sum over all probabilities equals to 1. So we get sum over j dpj is 0. Okay. So we can write dp1 plus sum over j, where j goes from 2 to omega, dpj is 0. So we take dp1 out of the summation. Okay. So we get dp1 is minus of sum over j goes from 2 to omega dpj. Okay. Now if we use this expression dp1 equals to minus sum over j equals to j goes from 2 to omega dpj, and then if we apply this relationship into the above expression of ds, we get 0 is ds minus kb dp1 ln p1 plus 1 minus kb times j goes from 2 to omega dpj times ln pj plus 1. So we get 0 is minus kb if we further simplify, we get this, or it says ln pj equals to ln py p1 or minus ln p1 equals to 0, as dpj's are not 0. So we get pj equals to p1, and this is valid, this pj equals to p1 is valid for all possible values of j. Okay. So we can write, so or thus we can write p1 equals to p2 p3 equals to p omega. Okay. So this is known as postulate of equal a priority probabilities. Okay. So this is known as postulate of equal a priori probabilities, which says for an isolated system in equilibrium, all microscopic states corresponding to the same set of a macroscopic observables are equally probable. Now, so we discussed postulate of equal a priori probabilities, which says for an isolated system in equilibrium, all microscopic states corresponding to the same set of a macroscopic observables are equally probable. So we got, or we have sum over j pj, where j goes from 1 to omega equals to 1. So you get p1 plus p2 plus like this, we get omega number of terms. So 1. Since p1 equals to p2, equals to p omega, so we can write omega times pj is 1, or pj so canonical distribution function. So canonical distribution function pj is nothing but 1 by omega. Okay, the microcanonical distribution function. So microcanonical microcanonical distribution function pj is nothing but 1 by omega. Now we arrived at the expression that p1 equals to p2 equals to p3 up to p omega by maximizing w, or in other way, in order to have the maximum entropy, the probability of the all states must be equal. Okay. So we can simply do, or we can simply calculate by considering three or four hypothetical systems. Like we have, so we consider a system with 4 states. Okay. And suppose probability of state 1 p1 we consider as 1 by 4. First we consider the probability of all 4 states are equal. So p1 equals to p2 equals to p3 equals to p4 are the value of all probabilities are 1 by 4, right. This is the case 1. Now we consider another case. Suppose p1 is 1 by 2, p2 is 1 by 4, p3 is 1 by 8, and p4 is also 1 by 8. So total probability again 1, and this is our case 2. So in case 1 all probabilities are equal, in case 2 probabilities are varied. Okay, so next we consider p1 equals to suppose 1 by 4, p2 is 1 by 16, p3 is maybe, okay, we will consider only 2 cases suppose, not 3 or 4 cases. We consider only 2 cases, case 1 and case 2, and then we calculate the entropy. So, we know S. So, S we just have seen the value of S is Kb minus Kb sum over j equals to 1 to omega Pj ln Pj. Okay. So, we will use that expression here. Okay. So, we have S. So, for case 1, entropy S is minus Kb sum over j goes from 1 to 4 Pj ln Pj. We get S is minus Kb times P1 ln P1 plus P2 ln P2 plus P3 ln P3 plus P4 ln P4. So, here for case 1 the entropy we are saying S1 here. So, we get S1 is minus Kb. So, 1 by 4 ln 1 by 4 times 4. So, we get minus Kb, not plus again Kb ln 4. So, this is the value of entropy for case 1. For case 2, we get entropy S2 is minus Kb and if we calculate this, we get S1 is greater than S2. Okay. So, maximum entropy we get when probability of all states are equal. Okay. That we prove now. So, we get probability. Now, we can calculate different thermodynamical quantities like S. So, S is minus Kb sum over j Pj ln Pj. So, we can further simplify this as S is minus Kb j goes from 1 to omega 1 by omega times ln 1 by omega. So, we get S is Kb and omega. So, this is the expression for entropy in microcanonical ensemble. Next, we can also calculate pressure, okay, average pressure. We know du is Tds minus Pdv. Now, since du equals to 0, so we get Tds is nothing but Pdv. So, we get P is T times del S by del V when energy and number of particles are constant. So, P is kBT del ln omega by del V constant energy and number of particles. Okay. We can also calculate enthalpy. Enthalpy H is we can also calculate Helmholtz free energy. A like A is E minus Ts, so you get E minus kBT ln omega, and so on.